So we have this. So we now have a panel discussion on unitarity, causality, stability. And the panelists here are Bianca, Dittrich, Donoghue, Alexey, Koshelev, Ivano, Basile, Steve Giddings. And we will proceed like yesterday. Panelists will make a short presentation. And then there will be some discussion between the panelists and with the audience. So first, in alphabetical order,
your audio is absolutely good. So maybe it's not. Yes, please.
Yes, so speaker.
No, just the audio.
The
The audio not on Zoom.
Yes,
Perfect.
yes, I can see that.
so first, in alphabetical order, Ivano, Basile. They come there or come there to the and use these to go backward.
Yeah. All right. Thanks a lot. Okay, it's visible. All right. So, what to say about unitarity, causality, and stability? What do they have in common? So why did the organizers decide to put these three words in the same panel session? Well, I don't know, but my guess is that they are something that we could call principles of physics. Now, principles, of course, must not be taken as like dogma or something like that. It's like, to me, it's the simplest set of ingredients that we can use to build more or less the structure of what we know, right, in physics, perhaps beyond. In particular, what I wanted to stress, the very practical thing about these ideas is that the whole structure of, the paradigm of modern theoretical physics, like the effective theory of, quantum fields, gauge fields, gravity, all of that, basically follows from these ingredients, right? It's the fact that the low energy dynamics can be reconstructed by these ingredients is very remarkable to me. Of course, when we talk about unitarity, we implicitly include the rules of quantum mechanics, right? When we talk about causality, here I specified, I'm not talking about cause and effect. I'm talking about the causal structure of relativistic space and time. That's what I mean by causality. Okay? So implicitly here, I'm talking about the rules of quantum mechanics, the rules of relativity, and the low, at least at the level of a weakly interacting system, the rules of the game are enough, constraining enough, that everything, all the low energy physics is pretty much specified by a few things. I mean, up to of course, the choice of details, like gauge groups or couplings and whatnot, but the broad strokes are there. And this, the remarkable experimental success of this approach, even if perhaps it's with a bit of hindsight, that I'm telling you that these ingredients give us this. I mean, of course, the historical route was very different. But nonetheless, this success of this framework and the conceptual, parsimony of it indicates to me that it's a good idea to take these ideas seriously and see where they take us, right? And this is what some people call, it's a notion of being conservative, and it has been called, being conservative in a radical way, in the sense that what you really try to keep is not how many types of quarks you have or how many dimensions you have or whatever, but rather the principles of the structure of the framework and see where you get. Now, I mean, I can say a few things about these three things and why they are particularly important. But to me, unitarity just means stuff makes sense, right? Like the information is there. It's not like just lost or created from nothing. And in particular, what concerns quantum gravity is that an actual proper definition of what unitarity means is way more complicated, or perhaps simplified, depending on how you look at it. in particular, it has to do with which observables are available. And the question of observables is tricky, but my standpoint is the way to talk about unitarity from observables that are available in gravity is through like asymptotic observables, right? Like S matrix in a broad sense. So it could be S matrix in asymptotically flat sectors or boundary correlators in asymptotically anti-de-Sitter, stuff like that. Perturbatively, you can do much more. You can give fixed diffeomorphisms perturbatively. You can talk about some relational observables defined by fields as coordinates, fields as clocks and rulers. So perturbatively, you can do this kind of stuff, and it was explained also this morning to some extent. I'm talking, again, because I want to see where the rules of quantum mechanics take us. I care about what can be said exactly, like in principle, of course. Like, yeah. And for example, a type of non-perturbative thing that can be actually investigated in practice, and it's a consequence of unitarity in the context of gravity, is a new type of gauge anomalies that can appear due to fluctuations of space-time topology. And they can actually constrain stuff about effective field theories, like global data, like kind of gauge groups that you can have, the number of chiral fermions of certain types you can have. So you can actually use this thing. It's not just philosophical musings, even though that would be pretty cool on its own. Yeah, so that's unitarity. What about causality? So causality we have extensive discussions about causality here, and I'm sure we'll have more. And I would say perhaps it's the weakest of the triple here, but I would still regard it as important nonetheless, even though in the context of gravity, it's a bit harder to define. Not impossible, I would say, but it's a bit tricky because, again, you have to phrase things in terms of the available observables that are present, which is not trivial, but I'm sure we'll learn a lot more about this from other discussions. As far as stability, you could just say, we don't live in a stable situation, right? Like the universe is expanding, etc., etc. That's true. So at the level of phenomenology, maybe it's not particularly important to talk about stability. So why is it on par with these other two words? My perspective is that stability is important on yes, Tom.
Just to understand the words, if you say the word stability what?
Right, exactly. To me, what stability means is that the theory has at least a vacuum, like as a ground state, right? That's what, to me, stability means. Like the spectrum is bounded from below. That's another way.
Always energy?
Yes, something like that.
Respect to what?
Right, with respect to the asymptotic boundary conditions.
If you don't have asymptotic boundaries?
Yeah, that's true. In my perspective is that those sectors are either completely absent, like you must have asymptotic boundary conditions to talk about all of it, or they are trivial in the sense that the Hilbert space is one-dimensional.
There's no quantum gravity in this region.
Yeah, what I'm saying is that such a theory would be trivial, like the Hilbert space would be in one dimension. But we can talk about it. But
We have examples where this is not the case.
Sorry?
We have examples where this is not the case.
Yeah, we can definitely discuss this. Yeah. But I understand it's a kind of a strong thing to say.
Quantum cosmology examples with the Hilbert space is definitely not one dimension.
Yeah, but I'm happy to discuss what the observables are. But anyway, so yeah, like this is my perspective on these 3 points. Now I don't remember if I have a second thing. Yes, I do. So what are some things we can say? Well, in the case of stability, we can talk about like what are some implications. For example, the existence of fermions could be like a necessity of stability. Or in the case of a 4-dimensional effective field theory, it could be that stability, as discussed in this paper, a recent paper by Basile and collaborators, may imply that the cutoff of the effective field theory must actually be small relative to Planck, right? Which is a non-trivial statement because the EFT normally has no information about what the UV cutoff is. As for causality, again, in this weakly coupled regime, it can be probed using S-matrix bootstrap arguments and calculations. And one way to avoid certain causality issues is to, either your theory is local, Or in the case of gravity, this seems to be this way out that recoupling is like introducing powers of higher spin degrees of freedom, which again it's a consequence of investigating a simple principle from very general premises. As for unitarity, again, I was talking about some new types of anomalies that were investigated recently. But also one can use, again, S-matrix bootstrap techniques to concretely study the implications of unitarity, to constrain what UV completions could look like, both perturbatively to see like, what the spectrum of the theory looks like, and non-perturbatively to see like what the bounds of on Wilson coefficients can be, for example. So yeah, that's all I have to say.
Okay, thank you.
It's something with the Zoom, when you move hands, it just leaves balloons.
Yeah, I noticed that yesterday.
Sorry, what was that?
It's nice.
Okay, so being the non-perturbative person, I speak a bit about the non-perturbative viewpoint. And so this is also in a situation where you do not have an asymptotically flat boundary. If you do have, I can comment on that in the deep. And so that would be the first comment is unitarity. Can we even define what it means according to like the non-perturbative standpoint? And so that is if you go on and quantize gravity, or Roberto would say space-time, either canonically or also via the path integral. You want to find solutions to the Wheeler-DeWitt constraints and to all the constraints. And then, the point where we would say we ensure a consistent probability interpretation is that you have to find an inner product on the space of solutions. Now that you might not really understand the significance of that, but there's kind of, again, examples in cosmology that people still discuss what is the inner product. So you do want to do that. You need to fine-tune to have enough solutions to allow for a semi-classical limit. What you usually have a requirement is that your observables have a reasonable representation. And later on, I might comment if you have a boundary and have a suitable definition of a so-called physical Hamiltonian, you might want to require that indeed this Hamiltonian is, for instance, self-adjoint, which means a unitary. But in general, you don't need to require that. So it's really this step of finding an inner product, which gets you to a consistent probability interpretation. And there's no time evolution yet. In principle, you can use the path integral. There's a more mathematical construction called the rigging inner product to construct a projector. So it's not a proper projector, but you have lots of infinite delta functions involved, which is supposed to project onto solutions. So roughly, if you integrate, for instance, over positive and negative laps, that's supposed to project you onto the Wheeler-DeWitt constraints. And it also provides you an inner product via the so-called rigging inner product. Okay, as I mentioned, there's a priori no time evolution. That's known as like frozen time formula. The wave function in itself already contains all the time evolution without needing an explicit time parameter. But what you can try to reconstruct via relational observables by identifying a set of clocks is a time evolution. And so you can, if you're gauge fixing, you can think of gauge fixings, you can understand it as a family of gauge fixings, with family meaning that the parameter which you can identify as a time parameter. And in this case, if you are lucky enough, you might find really the so-called physical Hamiltonian, which would be really also another observer which generates the time evolution via commutator in the usual sense. But as I mentioned yesterday already in the presentation, well, it's not obvious that there are good clocks or perfect clocks. There is physical systems which always would move forward. At least if we are in a closed universe. If you have asymptotic boundary conditions, you can possibly use that to define a time, and then you have this global Hamiltonian. But if you use kind of relativistic fields, and typically they include points in phase space where the clocks start to go backwards. And well, some people, in particular Boyo-White, Philippine, and others, and Boyo-White continues to do that, investigated a lot what are the consequences. And one example, in particular, if you have these kind of Umkehrpunkte, so these points where clocks go backwards, that leads to appearance of non-unitary effects, which if you believe in your clock, and it suddenly starts to go backwards. So in general, we expect to be able to reconstruct time evolution only in a semi-classical regime. And so in summary, it's basically that you first have to kind of reconstruct time evolution in quantum gravity. That might not be possible to all scales, or it might only be possible in a semi-classical regime. And therefore, it's not very clear what does unitarity mean. That does not mean you have an inconsistent probability interpretation, because as I mentioned, that is addressed by finding this inner product on the space. So we have a Hilbert space, and from that you have to reconstruct the time evolution. One particular example of, well, and where it's a bit unclear what is time evolution is a no boundary wave function. First of all, you don't have an asymptotic boundary, and secondly, well, the lower part of the solution comes from an Euclidean settle point, so it's also not very clear what time is there and there. And the second point I'm making here is that there have been suggestions that you might want to even extend the concept of unitarity, and a big extension of that is to replace it by the requirement of isometry, but even that you might not want to keep that. And this applies in particular in discrete frameworks, but you want to describe an expanding universe, but at the same time you want to keep your discretization scale constant. Or if you say of a cutoff, you want to keep it constant. And so that, of course, well, applies to discrete frameworks, like I'm doing, but Jordan Kotler and Andy Strominger also proposed that, and they're motivated by cutoffs, in particular with respect to entanglement theory. And can you formulate that consistently? And the answer is yes, you can. You can basically even consider both cases that you add degrees of freedom during time evolution, or that you remove degrees of freedom, that your universe shrinks again during time evolution. And so if you only have expansion, you can say you actually replace unitarity by isometry. In fact, Kotler and Strominger were basically inspired by so-called tensor network pictures of quantum gravity, where in tensor network algorithms you always have isometries, or in so-called quantum error correcting codes. But you can also consider a contraction. It's a bit, well, there's a philosophical interesting aspect. You can only do that, you can only reduce kind of the number of degrees of freedom if certain constraints need to be satisfied. The constraints are actually that the state you want to erase has to come from basically the time reversed state you get by if you add degrees of freedom. And so also the state is determined completely by the action or the path integral. So it's kind of one way to try to construct a vacuum state. It's very similar to the no boundary proposal. You add additional degrees of freedom in a preferred state, which is determined by your action or your amplitudes. Okay. Another point, which is separate from that, is on the causality and topology change. If you have topology change, I don't know whether it's causal or non-causal. So for Renata, this is non-causal because causal dynamic triangulation for which causality change for the sets.
Lorentzian structure, classically
for causal sets, that's allowed according to P. So there you see if you have topology change, you are Lorentzian, you have these points where you do not have a well-defined Lorentzian structure in the sense that you have more or less than two leptons there. So you have what we call light cone irregularities. And as far as I know, they are really connected to topology change. However, they can also appear without topology change. For instance, they would replace in the discrete the essential singularity at n equal to 0. If you consider, for instance, models in cosmology and integrate out certain degrees of freedom, you get your action within 1 over n term and leading to an essential singularity, which makes actually the Lorentzian path integral not necessarily unique. Interestingly, these light cone irregularities, if you are really Lorentzian, they lead to branch cut and imaginary terms in the action. And so that's what you don't see at all if you are Euclidean. And they're essential for computing entropy from Lorentzian path integrals. And so you have various aspects of possibly being non-causal because you have branch cuts which are non-analytical. You need to choose which side of the branch cut you want to integrate over. And you have imaginary terms, which then lead to at least what looks like very non-unitary effects. Okay, thank you.
Use these two.
Oh, those two.
Yeah.
Okay. Thank you. So I'm just going to focus on unitarity and causality. I'll have enough to say on those and won't say much about stability. So first, unitarity, and this has already been touched on. Formulating unitarity is a little bit challenging in gravity because it relies on understanding more about the nature of evolution and the nature of observables in the theory. As has already been alluded to, this connects with the problem of time. So for example, if we were to write unitary evolution operators like were discussed this morning, you give those as a function of time arguments, but of course that's not a diff invariant thing in quantum gravity without some more care. So that's part of the problem. So how do we approach the question of unitarity? Well, for one thing, there's pretty good evidence that at least something closely approximating flat space is an actual reasonable quantum state for quantum gravity. The curvature radius, say, associated with the cosmological constant, is much bigger than the Planck scale. That factor is around 10 to the 30 or something. So that at least suggests that while we don't live in a state of quantum gravity that is exactly Minkowski space, we're pretty darn close, at least if you go out into vacuum away from matter and so on. So it seems like a reasonable assumption that in quantum gravity, we have at least to a very, very good approximation states which correspond to flat space and excitations of flat space. And then if you think about quantum states that are excitations about flat space, you can study the S matrix of involving those excitations, and you can formulate unitarity in that context. So that's one sharp way to try to go after the question of unitarity in quantum gravity. Now, of course, there is another subtlety that it's hard to define the S matrix for four-dimensional quantum gravity. One way around this is to, if we can formally, or if we believe that there is a solution to the problem of quantum gravity that's valid in other dimensions, and if we work in a higher dimensional space-time, we can get around the various infrared problems. Or one can try to figure out how to give a careful definition of the appropriate generalization of the S matrix, including soft gravitational effects. Another approach is to think about different asymptotics, for example, anti-de Sitter space, although there are some non-trivial questions about how to relate that to, say, flat space scattering. So it's not completely simple and uncomplicated, but nonetheless, let's assume that there is a reasonable approach to formulating the S matrix through one of these different things I've listed. And so we can study the problem of unitarity in quantum gravity in an S matrix kind of way. But then really we encounter the big puzzle, what I think is the big puzzle, which is unitarity in high energy scattering. I mean, ultra high energy as compared to the Planck energy. And there is pretty good evidence that we form quantum black holes in appropriate scattering experiments. And so we encounter this profound issue of how do quantum black holes evolve, and how do we end up with unitary evolution in particular in that context. To make a long story short, since this is just supposed to be a few-minute discussion, the apparent conclusion that I think a number of us have reached in different ways is that in order to make the story of quantum black holes unitary, you really need some modification to the principle of locality at long distances, not just Planckian distances, but distances comparable to the horizon size of an arbitrarily large black hole. And that's pretty ultimately radical at least in the local quantum field theory perspective, and is likely, in my mind, an important clue for the fundamental structure of quantum gravity. And we have not completely figured out what this clue is telling us yet, but I think we're headed in that direction. Okay, so now I've touched on non-locality. Let's come to causality. There's a standard argument that non-locality leads to a causality, which you can run, but you really, at least in the standard way of doing it, you run this argument using the symmetries of flat space. So in other words, non-locality does not necessarily imply a causality in the general context, it appears. So if there is some new kind of gravitational non-locality, what is the status of causality? Well, first of all, coming back to microcausality, which we also discussed this morning, microcausality apparently fails in quantum gravity. So this nice notion we have in field theory is gone because there are no local gauge invariant observables in quantum gravity. And you can formulate gauge invariant observables, but they're very non-local. For example, gravitationally dressed observables. And when you look at commutativity of gravitationally dressed observables, the gravitational dressing, the part of the operator that creates the field going out to infinity, basically spoils space-like commutativity. And you can see that quite explicitly, for example, in this reference that I've given. So we don't have a formulation in those terms. And so that raises the question, how do we really think about both locality and causality carefully once we're considering gravity as opposed to quantum field theory? What structure is it in gravity that implies locality, at least in the local quantum field theory approximation, where Newton's constant is basically taken to go to zero? Another way of phrasing it is, in gravity, how do we define mathematically the notion of a gravitational subsystem? That's something we can define we typically do define in ordinary quantum mechanical contexts. And it's something we can define in local quantum field theory in terms of commutativity of algebras of observables or subalgebras, as we discussed this morning. But in gravity, it's not so clear exactly how we should define the notion of a subsystem, localization of information. But coming back to also what we said this morning, causality is in cases where you think about it, say, in quantum field theory or in some modifications thereof, causality is generally important for consistency. Generically, if you violate causality, you run into paradoxes, and you can formulate various versions of that. We touched on the grandmother paradox this morning. So you need something, it seems, that would replace causality and avoid that kind of problem in your theory. And so there is a question, again, I think in gravity in general, about what it is that is essentially avoiding this kind of trouble. One place we can study that is coming back to this description in terms of the S matrix. We can investigate what the meaning of causality is in that limited context. And one way of going after that is, again, looking at analytic properties of say, the S matrix. And in particular, there are arguments that causality is associated with polynomial boundedness of the S matrix in the real negative T regime with large imaginary S, for example, referring to the Mandelstam parameters. So polynomial boundedness in that regime looks like it's at least part of the story of causality. You don't have time advances in scattering, only time delays is another way of putting it. There is a longer story about how you could, coming back to this first statement on the slide, how you could basically begin to reconcile causality with a lack of locality, which is part of this discussion of the analytic property of amplitudes. There's more on that in these last two references, but I think I've used up most or all of my time, so I'll just leave it with those few comments. Thanks.
So the other two panelists don't have slides, but so yeah, good. Alexey.
So yeah, so actually I was also confused without this combination of causality, unitarity, and stability. So I will start with stability because I don't understand how it is included in the set. But my take on this particular word of stability is, and actually I agree very much with the question of Thomas, stability with respect to what? What do we have? We have, at best, we have asymptotic states, if we can define asymptotic states. Yeah? And I think in principle, stability, of course, it's a good thing to investigate, but before we investigate stability, we indeed have to answer the question of Thomas, stability with respect to what? Then we can talk about stability of any construction of our theory, especially quantum gravity, because we have much more challenges. Okay? And so this is the most ambiguous thing to me, because I don't know how to answer this. question about stability with respect to what, because the only thing we should know, there are asymptotic states, but the problem is that it's not very easy to reach asymptotic space, and especially in time, and we don't know what we are talking about. But when we are talking about unitarity and causality, here things are a bit more transparent to me. This I don't know, and this I would be happy to learn from everyone what do they think about stability. But unitarity and causality, this is something I understand a bit more, I hope, at least from quantum field theory perspective and related to the discussion of yesterday, which was about quantum field theory with respect to description of quantum gravity. I stay on the point that quantum field theory is an essential ingredient, and therefore I'm happy to use tools which we already know from quantum field theory. And in a local quantum field theory, in Minkowski background, unitarity and causality proven to be good things to work. Okay. So now the problem is that we are moving to gravity and we are moving to curved space-time. Okay. And we are moving on top of this perhaps to not only we are moving to some generic curved space-time metrics, we're also going to perhaps different topologies. And this is neither to say that the dimension is not obligatory equal 4, and according to many references, not obligatory even integer. And even there are nice papers on the market, like from, for example, from my advisor Arefiva, who claims that dimension less than 0 is also makes sense in order to describe entropy of black holes. So in principle, I would say that these are much more subtle now questions what to do with all of that. But my take on these particular two things about unitarity and causality is two. Unitarity is often understood like S equal 1. To have this, by the way, you have to define S. Yeah? So in order to speak about unitarity in the sense of quantum field theory, you have to define what is this matrix, especially not in a flat space-time. And this is already not an easy question, and a lot of debates are around this. What is S matrix? Yeah? Needless to say that we don't know what is time and unitarity with respect to what. But causality is a thing which and I mentioned already during my talk today, so this is why I resorted not to do much slides and not to speak too much now. Causality is something which I think is the only, it only has unfortunate fate that which we can give up a little. We can give up a little bit in micro scales, as long as it is micro scale, so it at scales which, let's say, much less L, where L is corresponding to uncertainty principle. As long as we are hiding violation of causality by uncertainty principle, according to many, let's say, papers, by the way, Anna mentioned today very nice quote, like resolvable singularities. Resolvable violation of causality. Resolvable or unresolvable means it's either hidden or unhidden by uncertainty principle. If it is hidden by uncertainty principle, which we consider like one of the fundamental things, and actually I don't understand why we don't discuss this instead of stability now, which also may have get modified. So uncertainty principle is something which is considered fundamental, and then as long as causality is hidden by it, it's okay, and this will not lead to time machines just because we will not be able to add up a lot of micro violations of causality to a big one. Or at least it will become a probabilistic and not deterministic thing. Okay? And in this regard, when we talk about these notions, my take is that this one should be preserved just because we know a lot of problems, how much violation of unitarity creates as long as we consider flat space-time. I'm not very much certain that curved space-time and different topologies and different dimensionality and different whatever, or maybe discrete space-time, so maybe other paradigms, will bring us more luck with violating unitarity. But causality, it can be hidden by uncertainty, and therefore here we can build up, and what, for example, I was talking in my talk, it was exactly talked about higher derivatives and infinite derivatives. From this perspective, I'm not afraid to include the infinite derivatives and send the derivative operators to infinite power, just because as long as I will be able, I know it will break causality, but also I know that as long as it will be hidden by uncertainty, I'm fine. Unitarity is a much more, tricky thing, and violation of unitarity is, I would say like this. I would not start violating unitarity as long as I'm not certain that I explored all the rest. So, staying from this, I'm happy to discuss causality and possible theories which are causal at micro level. And with unitarity, I am happy to have this equivalence, this equality as dagger S equal 1. My only problem is that we have to start with definition of S matrix, which I would be happy to discuss about S matrix in the curve space. So this is what I want to say, and your critics as well.
That's all right. I'm not going to have anything. I'm just. So I've also had the opportunity to say some of the comments that I wanted to say in my talk yesterday. So today I'd just like to do 3 short stories to transition from yesterday's discussion to today's. The first short story is about a UV completion that's not mentioned at this conference. I've not been mentioned at any conference for the past 30 years. But nevertheless, it tickles my fancy. I like it. And it's, I think, my reason for bringing it up is I think it's a good thing to keep in mind about the present trends, and it's not necessarily the only possibilities. And this is Holger Nielsen's random dynamics. Okay, the idea is that at high energy, everything happens. There's all the fields that you want, and they all fluctuate as wildly as you want. It's totally random. But it has a consequence is that most of those fluctuations are only possible at high energies. The only things that can survive at the low energies are things where those fluctuations are protected by symmetries. So, for example, chiral fermions, their energies are protected and can emerge at low energy. Gauge fields, like U1, S2, S3, are protected by symmetries and can move at low energy. And so this gives you a hand-waving way of saying everything happens at high energies, but at low energies, we have a principle that tells us what our theory can contain, and it just happens to contain the ingredients of the real world, aside from the Higgs. But the Higgs, maybe it tells you is we need to find some conformal symmetry or something that protects the Higgs until it gets to low energies. So it's not, I think of this as a way. Maybe we don't have unification of symmetries. Maybe it's just the reverse. This is called at high energies. It's the lack of symmetries, and the symmetries emerge at low energies. It's the emergent issue scenario. And so it's basically you keep it in mind as a framework that we haven't been discussing at all, and there's none of the. The second short story.
Sorry, so for the case of gravity, what would you have in mind?
Yeah, I'll come back to that in a second. Yeah. Okay. The second short story has to do with reading some historical material by Diego Gabriel Roberto and I are writing a paper on two-dimensional nonlinear signal models, which are also asymptotically free, and it's forced me to go back and read some of the old papers by Landau and Pomeranchuk from the 50s. And in the 50s, they were constructing beta functions. And they were calculating all the beta functions and finding that they're positive. That's the story. And we now think this is the origin of the Landau poles, but they were using it for something different. They weren't using it for the running of renormalized couplings. They were using it to explore the relationship between the couplings and the bare couplings. So how does the bare coupling behave? And if you do this, they smear out an electron and then take the limit. If you do that work, you find that the bare coupling flows to zero. And so they conclude that all field theories are trivial because they have zero bare coupling. And this was used to argue that field theory is not going to be a way to describe the world. Field theory will fail. And it was quite influential at the time. Now there's flaws. Of course, one is that they missed out some freedom in Yang-Mills and nonlinear signal models. But even more importantly, the idea can be true. For example, in lambda phi to the fourth, it's proven that lambda phi to the fourth obeys this when it exists on its own. It's trivial. Yet, nevertheless, it's an eighth sector of the standard model. We use it in our present theories very successfully. And so the flaw is basically that there was a really, really solid calculation, yet the interpretation was incorrect. And I was feeling that many of the things that we also say, we do thought experiments like this, they also have potential flaws. So you have to keep this in mind as we proceed. So how do we proceed? Well, everyone has their own favorite way of doing that, and that's my favorite way. I'm a phenomenologist at heart. And I looked at the standard model, and it's a closed, self-consistent layer of reality. Basically, I don't really have any expectation that it's the final theory. Maybe it's string, maybe it's random dynamics, but it's closed and self-consistent and valid at some energy scales. And that's good enough for me. And I'd like to make the case that there's a possibility, an urgent possibility, that we might be forced into such a thing in the case of gravity. And this comes from the theory of inflation. If inflation itself may be incorrect, and Neil will probably tell us about tomorrow, but let's for the moment assume that it's correct. The simple models, the ones that make sense of inflation, like phi-squared theories, have been ruled out by experiment. And if I, as a field theorist, and probably most of you, if you look through the space of remaining theories, only one really makes sense to a field theorist. The others are controlled, and that's Starobinski inflation. Starobinski inflation has a very natural field theory interpretation. But if that's true, you're in a region where you're not yet talking about strings or anything. You're really talking about the metric. And it has to be dynamical at that scale. It's not just an effective field theory. The curvature squared is really a new dynamical degree of freedom that's there. But moreover, it probably can't exist by itself. For example, the beta functions that Roberto gave mix the couplings of the Basile squared into the R squared terms. And for Starobinski inflation to occur, the curvature squared couplings have to be, well, small or big, depending on where you're doing the inverse. But they imply that the inflation is happening well below the Planck scale. for this running behavior to occur, the Weil square also has to be living well below the Planck scale. It's only halfway below because it's the square of one coupling gives the running of the other coupling. But it's also well below the Planck scale. So we're going to be in a region, and if in Starbinsky is right, we're going to be in a region where we have quadratic gravity. And it's forced on us, and it's not resolved by random dynamics, strings or causal sets or anything. This is our little closed, self-consistent layer of reality. This is what might emerge from a theory. I can be totally agnostic as to whether it's the ultimate theory or not. It's the theory that we have to go from that region up to the Planck scale or to whatever the real UV completion is. So, but that's an urgent question now, because that's within our eyesight. And it brings in these issues that we were discussing today. In particular, it seems to me that the major issue that's brought in is this issue of causality. I think, the other things in a space that's as mildly curved as early cosmology, well below the Planck scale. This one has causal issues that were part of the description that I gave. And so the question, it's urgent then for us to understand that. And then the issue is, can we see it? Can we use it? Can we see it? I don't have an answer yet. Maybe we have. Can we use it? Well, one of the things that this type of causality does is it does interactions outside the light cone. And so, in fact, it's very good at making, well, it's not how good, it's good, possible to make things uniform outside the light cone. And so one of the things that might be useful for is starting inflation is actually very difficult because it actually requires a more or less uniform state to be prepared to start inflation. If it's too wildly curved, the inflation doesn't start. It's at least over one Hubble scale at that time. And so maybe this is useful in starting inflation. And if you're even more radical, you might say maybe this can replace inflation, because remember, one of the motivations for inflation is if you look over here and you look over there, those regions come from causally disconnected parts of the early universe. But if the early universe has some acausality in it, then maybe those regions could have been correlated to begin with. Maybe you don't need the inflation. So, but anyhow, I think if Starbinsky has some validity, we get forced into the issue of understanding causality in the early universe. That's my motivational speech.
Well, thank you to all the panelists for their interesting insights. And at this point, if any of you has comments on what the others said, it's a good point.
I don't know what you mean by unitarity turned into isometry. I would like to have you explain the terminology.
I have the same questions.
Yeah.
Oh, so sorry. Right. Unitarity, in particular, if you're in a finite dimensional Hilbert space context, that like the dimension of the Hilbert spaces needs to be the same.
Okay.
Isometry, that is not necessarily the case. So an isometry, A can map from a Hilbert space of dimension n to a larger dimensional Hilbert space. And so the condition is that the norm, is it the norms are the same?
Yeah.
The norms are basically the same on both sides.
The norms of what?
The state.
The state,
So
vectors
under some time evolution.
Oh, so, no, yeah, you don't need so technically you don't, I mean, technically it's just a mathematical definition.
Okay.
first of all, it's for maps from one Hilbert space, in this case,
Okay.
larger dimensional Hilbert space, and then time evolution comes in if you speak about finite time evolution steps. So in that case, you say the map which implements this finite time evolution step. Well, for instance, I didn't say that. It's Jordan, Kotler, and the Struminger which proposed that should be an isometry.
A simple example is if you again think about finite dimensional Hilbert spaces and say just qubits or something, you have some states in an n-dimensional space. Just tensor in a Bell pair, and then you've got a bigger space, but you're tensoring in a sort of a trivial state. But then you can think about how the original state embeds into the now the higher dimensional Hilbert space, and you preserve the norm and so on.
Yeah.
That's why it's isometry.
So you add new degrees of freedom.
But you've added new degrees of freedom.
And in that case, like the state in which you add new degrees of freedom is determined by your prescription. Kind of, if you have an action, it's basically coming from the exponential R to the action.
And that's supposed to be some dynamical process that you sort of create this entangled state.
Well, I think part of the motivation is what actually happens, when we study, say, either Hawking production or production of, perturbations in the inflationary universe, because, roughly speaking, if you think about evolution with respect to the cutoff, we have some degrees of freedom and say we've, populated them by, evolution up to a certain point. And then the next step is something like the Minkowski vacuum in the higher, above the cutoff comes down and becomes something like a Bell pair in terms of the lower energy degrees of freedom, right? So that's sort of the toy description of the Hawking process, or the process which produces, its perturbations in the inflationary context, which is analogous.
Yeah, so certainly, if you're in a discrete context and you want to have an expanding universe, but keep your fundamental length scale the same, but then you need such an expansion, and you have to add new degrees of freedom to do that. In this context, Struminger and Kotler argued also with the entanglement definition that it needs a cutoff, and if you want to keep the cutoff the same, I think it was motivated a lot by the so-called multi-scale entanglement renormalization schemes, where if you look at that, it looks a bit like an expanding universe, and there you add degrees of freedom exactly by these isometries and so-called entanglers. So like evolution. Yeah, it was first not written down as a time evolution, but there's kind of some radial evolution, and it has two elementary things, and one is this entangler map, and the other is isometry.
Yeah, I can see this in a discrete system in some sense. Continuing the way I think of.
But yeah, certainly. It's much harder to.
I don't quite see.
It's not. Yeah.
Especially if I can do different variants.
It's much harder to imagine that in a Hamiltonian description with a continuum time evolution, how that should look like. Maybe the Hamiltonian is apparently they're not self-adjoint in the usual sense. So I don't know.
There's a follow-up question by Thomas.
I was wondering whether this isometrical evolution is also invoked for closed universes. The reason I'm asking is if you think of global de Sitter space, then that's expanding, or it also has a contracting branch.
Yeah.
But the curvature radius, the 4D curvature radius is always the same. And hence the standard argument is that if you think of that as counting, say, the dimension of the Hilbert space, like the Sitter entropy, that doesn't change in global de Sitter space, right? So would you say that one would invoke isometrical evolution for I don't know, global de Sitter?
Yeah, my first remark, this definition of this proposal of replacing unitarity with isometry, that came in this particular paper by Kotler and Strominger and would allow only expanding universes. I mean, or it would only allow to add degrees of freedom.
But they did basically apply it in that context in the.
Not well, yeah, technically, I don't remember what they said about contracting. You know, I had a discussion with Jordan. I don't remember what he was saying about contracting. You know.
But in answer to his question, they, at least one of the contexts that they, I think, essentially were considering, you know, is de Sitter evolution.
Is de Sitter evolution. So for my,
in the expanding bit.
That's not global de Sitter. So then it's not necessarily a closed universe.
Well, it could be at least being agnostic about what happens before a certain time, you know, you could think about the portion of de Sitter space which is global and expanding.
Yeah, but even if you think of de Sitter, if it takes a no boundary proposal, where you start with, you know, no degrees of freedom at all, and then you suddenly go to a number of degrees of freedom to something. So that is certainly like an extreme example of changing the number of degrees of freedom. And so that's, you know, the no boundary proposal in the context of de Sitter would mean it's use Euclidean half sphere. So you do have one step where you go from 0 to the minimal radius and introduce a lot of degrees of freedom. So this step.
Okay, you want to change topic?
Well, related.
Related to it.
Just wondering, like, okay, well, one comment is basically you're taking no boundary proposal, which is in Euclidean time, and the question expanding universe, not.
Yeah.
So it's like comparing the answers you get from like maybe it's like apples and oranges.
Again, I've done the calculation in the sheet. You can write down a no boundary proposal, and you go in one step, which has an Euclidean time step, but then you define that as a state in your Lorentzian universe.
Okay, well, my question is a bit different, but still related to the same topic. So basically, we had many of you mentioned the S matrix. If you take expanding universe and you take a quantum field in an expanding universe, when the quantum field exits the horizon, which happens during inflation, it becomes classical. So your quantum system is defined by this boundary, the particle horizon. So whatever is inside is quantum. So now, why can't we ask a simple question? How collision happens within the boundary? I'm using the word collision. I don't want to call S matrix as asymptotic states and mathematical definition. But let's ask a physical question. You have a space-time boundary. Before the quantum states leave the horizon, does it deal with collision? Some collision of states. Whatever we want to. Let's say I'm using a very simplistic language. At the end of the day, what S matrix describes is how particles collide, how particles interact, and just get scattering amplitudes.
Okay. Localize this, no?
Yeah, locally. And because once the states exit the horizon, it's not part of the quantum system. You get classical. Their fields become classical.
Well, yeah, I mean, I heard a talk that they advertise in cosmology. Indeed, for this reason, you should actually apply the theory of open quantum systems.
Well, it's not open quantum system because once the state exits the horizon, it's not part of the quantum system anymore.
Well, that's an open quantum system, yeah. So where you have an environment which would be outside the horizon. Yeah, I mean that comes to this definition. If you say collision or having boundary, I mean it's kind of the boundaries.
Collision of particles. Okay, well, I understand the particle definition becomes.
Our definition.
Let's see, we encode space-time. We cannot call particles.
Yeah, but in my understanding, our usual definition of collisions is exactly what the S matrix.
Yes, then you say, well, then we jump to infinite times. Okay, let's not jump to infinite times. We have quantum states spending some time, interacting, evolving, while they are within the boundary. Okay, once they exit the boundary, then they become classical. So how to deal with them is a separate question. So,
well, you can still
infinite
describe them as quantum states. It's just there's a decoherence that takes place once they're outside.
decoherence takes place. So,
But they're still treated or can be treated as quantum states.
yeah, you can. No, you mean once the decoherence happens, you still want to treat them as quantum states.
Yep.
There is no evolution, I guess. So that answers the truth. Yeah, at least if you to study free particles there, I'm sure it's frozen on superhorizon scale. So
Yeah.
you don't worry about them much. But I'm saying that let's not worry about the infinite times. We can maybe able to do finite time processes in a curved space time that will give us answers.
I understand here as a proposal which I need some people to define local subsystems.
Yeah.
In the case of scattering, I guess the main question would be, like, we do that scattering with asymptotic states and so on to have isolated systems, I guess. So for local systems, that's not a given. And then you still need for the local systems to say what are the boundary conditions, or should you treat these classical in a classical way, I guess. If there are boundary conditions, we would treat them boundary wise. But then since you don't have an isolated system, we haven't turned off what is happening, I guess it's all more complicated.
Yeah, so that means that definition written there as matrix, it has to be modified, it has to include horizons. Somehow, we don't know. I agree that it's a difficult problem, but I'm just trying to pinpoint the way we write is always like this, but that is in the QFT in Minkowski. But if we are dealing with curved spacetime, all the questions we pose are issues with curved spacetime.
Yeah, no, I agree. That's why I make like non-perturbatively, or if you're not in flat space time, even with what does scattering mean?
This can scatter discussion.
Another one or two?
Question.
Unrelated. So just to close this, I don't know if you want to close, but on this topic of this geometry and maybe. I was not aware of this idea that you can add degrees of freedom. I'm reminded now of this proposal of Hoyle in the 1950s, I think, of continuous creation. Is that legitimate comparison? Because that was rejected violently, I think.
I'm not so familiar. I wasn't born yet, so exact proposal. It was added as a new degree of freedom.
Yeah, there's a superficial similarity, but I think the objections don't probably apply in the present case. But anyway,
would be interesting to know why.
Yeah.
Okay, let's stop it here. Renata, maybe?
Yeah. Sorry, just to let you know, there's also online a question.
There's a question on this topic?
I don't think so.
Well, then let's have Renata and then the online question.
I wanted to return to the question I asked you, John, which I thought you would then answer in the remainder of your presentation, but I didn't catch the answer.
Yeah, the answer is basically so if you want to have a protected sector in the gravity sector, one possibility is the gauge symmetry and renormalizability of quadratic gravity. That becomes its own little closed sector. And so my third little story there was arguing that perhaps we actually have to face that little sector, which from my viewpoint emerges naturally from Holger's random dynamics, because it's a protected sector. It's a renormalizable sector of the metric.
Okay, but so symmetry is not to be taken very literally.
What is it that protects the masslessness of the graviton, it's the diffeomorphism symmetry that we had built into the theory. So
Can I rephrase? But you're invoking it less as a technical concept, as more as a moral principle, because I mean, I think this idea is very fuzzy, right? Apart from the set of more random objects.
It's certainly very fuzzy.
Yeah.
Which is why it hasn't been discussed for the past 30 years.
That's right. So, but you encourage us to take up old ideas.
Right, but right. But I do think that at least in my reasoning that it has some connection to make me look at theories that aren't necessarily unified together into larger theories like you might do in string theories, where everything comes together with a higher symmetry. But I'd like this idea of the little closed sectors, which are at least temporarily protected sectors, and that turn into whatever the final unified theory is. That's at least in my mind, that's the case.
While we're on this subject, I actually had a question come up in my mind when you were discussing this random dynamics. So you said the proposal is roughly that everything happens at high energies. Right. And when you say at high energies, are you equating that with short distances or? Yes, okay. So that's one of the things that I think gravity is teaching us something new about. That again, high energies should not be equated with short distances. High energy should be equated in some sense with long distances, because if we try to make something with very, very high energy and try to make it in a small region, in fact, what we do is we make a big object, a big quantum black hole or something like that. So that's part of the paradigm, I think, that we should be grappling with in thinking about quantum gravity. And so I was trying to figure out how that would relate to what you were saying. It's in some sense, there may well not be scales smaller than the Planck scale, and put differently, if you think about very high energy scattering at ultra Planckian energies, you start probing longer distances. Things turn around.
I agree. It should be so scale.
Right. As we just do. Some of these ideas only make sense if the gravitational reaction becomes weaker. Or these processes become less important high energies. I can't guarantee that that's what's happening, but it requires some modifications.
When you say that, do you mean the gravitational coupling is a function of S or is a function of momentum transfer?
Yeah, no, I have more in mind a problem of the theories that in the category that I was discussing last time, which is the amplitudes naively start growing, and they grow power law because there's momentum dependence in the amplitudes, and independent of whether the couplings run logarithmically some way, but the power law, and that was an issue that I thought we need to grapple with, and there is a proposed solution out there by Holton that I described, which would have the effect of actually, would convert all these growing power laws into things where there's a lot of cancellations and the amplitudes actually get weaker. I don't know, I have been myself a skeptic of that. And if there's not some solution, I might be giving up on these theories. But this would be required in order to make the picture that I was describing make sense.
So that would be, well, for example, if we thought about large S scattering a fixed angle or something, that would be some big modification.
Yeah, it would be, right. So normally those amplitudes grow. Yeah. And we have to find a way to have that not happen.
Yeah, okay, yeah.
So maybe we can have the questions from
Philip Mannheim.
Okay.
I asked Philip to unmute.
Yes, good afternoon or to you. Good morning from me. I wanted to comment a little bit on higher derivative gravity. John mentioned Starobinsky is one possible way that we might need to think about it. And Roberto and John have looked a lot at higher derivative gravity very extensively. But what I want to point out is that it's actually not just a problem for gravity, or it's not just an issue for gravity. If you take the standard Dirac action coupled to the spin connection and give the fermion a mass, and you do the path integral over the fermions, you generate a fourth order gravity plus second order gravity theory. You can't avoid that. That's just doing the fermion path integral that we do all the time. So you have to deal with higher order gravity, whether you like it or not. Now, if you don't like it because you think there's something wrong with it, like it has states of negative energy or states of negative norm, then you're saying that the standard model is destabilized when it's coupled to gravity. And you have to deal with that problem. So the question is, can you deal with that problem? And that's some work that I started with Carl Bender. And what we noted was that you can't just worry about the propagator, you have to construct the Hilbert space. And when we constructed the Hilbert space, we found that the Dirac norm was not just negative, it was infinite. And therefore, we knew we were in the wrong Hilbert space. Earlier speakers this morning talked about the issue of getting the right inner product. And what we found was that there was a different inner product, which was the overlap of a ket with its PT conjugate ket. And that norm was positive definite, and the theory is well bounded and stable and causal. So I think there is a procedure for constructing a fully renormalizable, causal, and unitary and stable quantum gravity theory based on second plus fourth order gravity, whose low energy limit is standard Einstein gravity. So I think that you should not dismiss these theories, because you'll have to deal with them even if you don't like them. Anyway, that's my comment.
Well, thanks, Phil. If I understand correctly, though, in what you say, these high derivative terms have to be introduced as counter terms because of the presence of the loops of matter. Is that right?
Yes. The statement is this: if you just, instead of the path integral, just take a one fermion loop graph in the presence of an external gravitational field. And what you do is you generate the fourth order action. So either the path integral, because it's linear in psi and psi bar, the path integral is equivalent to a one loop Feynman diagram. And also, the nice thing about Feynman diagrams is you don't leave the Hilbert space. So if you start out in a Hilbert space of standard gravity where all the norms are positive, you can't lose that by doing a perturbative loop in an external gravitational field. Therefore, the theory must finish up unitary. That's the argument that Carl and I have been making.
Anybody here wants to comment on that?
I mean, I just think if you integrate out massive degrees of freedom, yeah, you produce this higher derivative sequence of corrections, but that's just how effective a theory works. There's nothing unusual about it, right?
Not changing the gravity.
I'm not saying it is unusual. I'm saying is you have to live with it.
Yeah, but we know how to deal with it. It's effective theory, no? I mean, maybe I'm missing something.
Yes, I also think we live with it. There is no problem. The only thing which I a bit skeptical that it's unitary and causal. If it is a derivative, it will be a causal anyway. The question is how much is it?
The answer is that by the time you reach the cutoff, which is the mass gap of the stuff you integrate out, you start, maybe you would resolve some of the size, but then the UV completion kicks in and becomes causal again.
Okay, if I can comment, if you have a propagator which goes like 1 over k squared minus 1 over k squared minus m squared, then both of those two pieces in the propagator are separately Feynman causal. They're just Feynman causal propagators. The minus sign, that's the relative sign between the two propagators, does not affect the domain of support of the propagator. So having the minus sign is not in itself a cause of a causality. The big issue is, what is the Green's function that you associate with that object? And that's the only place where I depart from what everybody else is doing in effective field theory. Most people take it's a matrix element of a time-ordered product between the vacuum and its Hermitian conjugate. And that's the object which is infinite, as well as having a negative piece. What Carl and I noted was that if you take the matrix element to be the overlap of the vacuum with its PT conjugate, then that quantity is a different Hilbert space, and then it's a completely defined theory. So the issue for effective field theory is, you've got the propagator, what Green's function are you relating it to? In other words, what is the Hilbert space that you're doing the physics in? That to me is the key question. And you can't discuss the theory in the Hilbert space where the inner product is the Dirac one, because that inner product is infinite. That's what Carl and I showed. So that I think is the difference.
Well, at this point, there was a question by
Comment.
Ivano.
Well, Damiana had raised it a bit a while ago.
It was related to what Ivano also said. I think that the point raised by Philip is very correct and very important. And I also keep forgetting about it myself, but it is very, very important, so I stress it again. So basically, consider quadratic gravity. If for some reason you forget about the cosmological constant because you don't want to introduce it, then renormalizability, not effective theory, it forces you to introduce it because you have to bury the divergences of that type under a new parameter. So there is a standard model, and the standard model has to be coupled to gravity. And if you renormalize that with the loops of fermions or anything, you will get R squared and R mu squared as divergences, and so you are forced to introduce new parameters in front of those. So you get to that theory as a fundamental theory anyway. And then you have to deal with it. But it's not an effective theory, so you are forced to consider it, precisely because there is the standard model.
But this is only...
You don't get the cubic terms, right?
No, I
you
understand.
don't get derivative, higher derivative.
In the framework of perturbative renormalizability, this is what happens. In the framework of EFT, this is not what happens. That I was just highlighting the difference. Like if you say something like you start from an EFT of Einstein gravity coupled to a massive fermion, which has some cutoff, right? And then you integrate out the fermion, then you generate a bunch of other things cut off at the mass of the fermion, but it's still EFT. It's just an EFT of an EFT. So it's completely like it generates no issues. But what you say is completely true. It's another context. Like I would just.
I think that Philip was
had in mind this kind of other thing.
Fundamental theories.
Perhaps.
We can ask him.
Well, I definitely meant it as a fundamental theory.
Then yeah, that's how it works.
Yes.
Yeah, I would just be commenting that the effective field theory is below the mass of this that's integrated out. And for there, you just use the neutral propagator. There's no issues about this.
Yeah.
And so it's only
And
when you're above it, you should be actually dynamically including that fermion in all the processes.
Yeah,
and,
exactly.
And then
Exactly.
so you shouldn't be integrating it out anymore and treat it as a full theory.
Precisely. Yeah, that's all I mean.
Well, I just get confused about people keep saying EFTs. I mean, if you have getting some renormalizable theory which has implications for cosmology like Stravinsky inflation, why do we keep worrying about EFTs? What is the use of EFTs?
What do you mean, what is the use of EFTs? The EFTs are a way to parameterize their ignorance about the microscopic.
Yeah, where do we apply it?
In all of physics?
Where? Give me an example.
The standard model.
Standard, well, standard model is complete.
No, has a higher
Complete
irrelevant
purposes, but if you say EFT, okay, extend it where you need to extend it, and you are using the word EFT in a vague situation, okay?
No, what I'm saying is that
Precisely
all of
what
physics
EFT means, where you are applying, where you are measuring, where we can measure like the future targets to see what signatures for EFT. And we have too many EFTs. Can we narrow down the EFTs for the future measurements?
Yes.
We have EFTs whenever we need them. We have the Fermi theory is one, chiral perturbation theory is another. You can make
but I'm talking about
gravitational
EFTs,
basically there's
below the Planck scale.
whenever it's useful, you do it.
Yeah, exactly. I don't see what the issue is really.
There's also another comment online. Take a look.
Okay, so
I'm not sure who.
online Thomas.
Okay. Philip, go ahead. Or unmute yourself, please.
Yes, thank you. I'd like to comment on the meaning of effective field theory. If we take the weak interaction, the fundamental theory is SU2 cross U1. It contains fermions and gauge bosons. Below the mass of the W, the effective theory becomes a 4 Fermi theory. So you can say that the 4 Fermi theory is the effective low energy limit of a renormalizable Weinberg-Salam theory. And that's not really an effective theory, that's just its low energy limit. When people are using effective field theory for gravity, I don't want to be unkind, but they have some idea that there is some fundamental theory for which that is its low energy limit. Except because they don't construct it that way, they call it an effective theory. Now, the theory I mentioned, which is R plus R squared, is a completely well-defined theory whose low energy limit is Einstein. So it's not as though we're doing fundamental theory at low energies. We're not doing effective field theories as a hope that it describes the low energy limit of some other theory. Now, the other type of theory I work on is the pure fourth order. Now, the pure fourth order has no fundamental scale. So there is no Planck scale. And therefore, the whole notion of talking about physics below the Planck scale, above the Planck scale, isn't relevant. So the Planck scale itself requires that you have a theory which is both second plus fourth, which I said before you will get from the fermion theory. So that's the one with the Planck scale. But if you just do pure fourth, there's no Planck scale to begin with. And that's why I worked on that theory from the beginning, because once there's no Planck scale, there's no reason for the cosmological constant to be Planck scale. And that's why I started working on pure fourth order theories way back.
Okay, there was Thomas.
Yeah, but I don't want to change the topic. So my question was more about other things that were said during the introduction.
I think we can probably change the topic at this point.
Yeah?
Yeah.
Okay, so the title of this thing is to do with unitarity, causality, and stability. And I was a little bit confused to see no explicit mentioning of baby universes. So if I understand the literature a bit, say in the 80s, early 90s, the creation of baby universes or not was considered an element, like a crucial topic to understand the notion of unitarity in quantum gravity. So I wanted to hear from the panel members whether, when they worry about unitarity, perhaps its definition even, whether they actually have this in mind as the main effect, namely the creation or absorption of baby universes.
So maybe I can just quickly.
Already touched upon yesterday. This was probably already touched upon yesterday, but
I think so. But really, like, my position is very simple. Perhaps I'm not that I'm an expert on this or anything, but I think the usual story that if you go through the alpha parameters of Coleman and you get this ensemble that is not unitary, I think the natural solution is just to say that the Hilbert space of baby universes has dimension 1. That's the way to just
Right, but I
preserve
often hear
unitarity.
it these days, and then people extend this to say that the Hilbert space of any closed universe equals 1, the dimension of it. And to me, it's completely unclear whether like a general audience would kind of find this an acceptable point of view. I'm just interested to hear people's opinion, because like in the swampland program, this became sort of mainstream thought, but I don't understand what people think outside.
But, yeah, if I can comment, I mean, this baby universe is often in a Euclidean context. I made that point in a Lorentzian context. Well, baby universes are connected with this topology change, and you get these interestingly imaginary terms, which to me look certainly non-unitary. So then this comment on, yeah, you made it also to one-dimensional, closed universes being one-dimensional. If a closed universe, you mean a closed spatial universe?
That's not what I no.
No, okay, so I just, yeah.
No, in that case, what I was worried about is more like what observables to define in a sharp way, like in a way that you avoid the intrinsic ambiguity of like if you probe a region hard enough, you make black holes and stuff like that. That's an observable
that's
thing.
Local observables. Okay.
Yes, that's but as far as now, I was talking about like other.
Okay, well, that was if there's kind of enough examples now for quantum cosmology with a number of degrees of freedom, where you can construct relational observables explicitly and do your quantization program and have you in the finite dimensional Hilbert space.
Yeah, no, but indeed this issue, the cosmology situation, was not connected to what I was talking about. I was but in this case, I would be curious to understand more of these observables in the sense that, like, if you build these relational observables, which perturbatively are perfectly well defined, non-perturbatively, how do you avoid the issue with having them sharply defined, which means like you can, in principle, compute them to arbitrary accuracy in whatever parameter. Avoiding the operational issue that if you try to measure them sufficiently precisely, at some point you make a black hole and you get an uncertainty of e to the minus blah over g Newton.
Yeah, I mean, okay, so that is in principle when I was speaking cosmological models, that is kind of what is called mini superspace, where you have like global observables. So it's this question does not arise.
Right. So global observables are fine.
Kind of, I don't know, you can take scale factor as a clock or something, and deal with that. Sometimes you do have global issues of different sectors of your solution space which you have to deal with.
Yeah.
What about
yeah,
the
but
dimension of quantum gravity?
Quantum
gravity has perfectly
2D gravity, yeah,
perfectly local observables.
Right. Indeed, I have no issue with such problems below 4D or 3D. And indeed, that's perfectly fine.
But
implicitly, I work at least in 4D because gravitons and black holes and all that generate these conceptual issues for me, at least. In that case, I agree with you. Yeah.
But I don't. The sharpness you mean because there are no black holes of the same nature in 2D?
Or gravitons like
so
stuff like that.
To be 4D.
At least, I would say.
You've still got to define, if you want good observables, you need gauge invariant observables. So which are you thinking about?
and out of the
endpoint functions, diffeomorphism invariant endpoint functions.
Endpoint functions of what?
Of what?
Of what?
Of the gravitational, whatever.
What operators?
What operators?
Yeah.
Curvature, global curvature.
The curvature at a point?
At the point, well,
Well, what do you mean by curvature?
Yeah, well, curvature is not a quasi-local thing, but of course, in order to make it diffeomorphism invariant, you will have to integrate all the insertions. Yeah. And that's
you can integrate over it.
I would say that's the best you can do. And I would say that's a feature and not a bug. And if you insist, on things like, I don't know what Ivano is hinting precisely, but just localizing things, well, that's you won't be able to do that typically in a kind of genuinely non-perturbative context.
Right. No, but indeed, I think in 2D, the story is pretty much fine because.
I'm talking higher, I'm talking 40.
Oh, sorry, then it's.
That
some
was my
typical mess.
point of yesterday's discussion, was that there might be no local observables to the degree that we can resolve.
Right, exactly. So that was my thing. Yes.
Yeah.
We're talking about like short.
Then we have to live with that. So they might not exist, but okay. So
I'm more inclined to go to asymptotic observables and say like, okay, then I hope that we have an asymptotic boundary.
Yeah, but why?
And then
why would you hope that asymptotically you want to go with like below Planck scale? I mean,
What do you mean, sorry?
Why do you need an asymptotic also like very far away and a resolution of Planck scale?
Yeah, as a way to have observables that are well defined, no inherent ambiguities of that kind. That's what I'm talking about. But
yeah, it's kind of
it's a way to go about it. It's not the only way, I suppose. But
Ivano, in your slides, you had some mention of some new gravitational anomalies.
yeah, that's right.
You didn't explain very well. Is this a breaking of diffeomorphism invariance?
You can say that. It can be also that. So they are a form of global meaning not small gravitational anomaly related to
not small. It means not for infinitesimal diffeomorphism, right, but only for large diffeomorphism.
Yes, that's right. That's right. They are large gravitational anomalies, but they are so the usual. If you want me to elaborate a bit on that,
yeah, I think so.
So the usual story that goes back to the 80s is that the way to capture such large anomalies in a way that also captures the small ones perfectly fine is to a construction called the mapping torus. So there's a sort of a D+1 dimensional manifold, closed manifold that captures a topological invariant of which captures these anomalies. Right? And again, in usual construction, the idea was that the operational meaning of this mapping torus is that you imagine you're able to do like a little a family of gauge transformations, so to speak. You do a loop in the space of gauge fields or gravitational fields, and you go back to the start, and then you see if your observables are shifted by a phase, right? And that would be an anomaly. Now, these were completely understood, by Witten and Alvarez Gomez and others in the 80s. But then people started thinking, what happens if, in some sense that is made precise in these papers, you add space-time topology fluctuations in the game? And what happens is that instead of considering this special type of manifold, these mapping tori, you get essentially any closed manifold that is available in your theory. Like if you have fermions, it should be a pin manifold. If you have oriented fermions, it must be a spin manifold, and so on, right? If you have a U1 gauge group, it should be equipped with a U1 principal bundle, and so on. So up to all this structure, now you have to evaluate these anomalies, these topological invariants, on more general manifolds. And the mathematical objects that classify these anomalies, these larger set of anomalies, is different. Instead of like specific homotopy groups, they are more, generally larger cobordism groups. And there can be new anomalies that were not there before. And sometimes there are concrete examples.
Okay, so, but apart from the mathematics, generally when you have an anomaly for the gauge group, that is the end of the theory, right?
That's what I'm saying.
If there are such things in gravity, then your theory is.
That's right. That's right. And in the standard model, no. Luckily, all these anomalies vanish, and it's a non-trivial result, right? It could have been different, but it's not.
you are saying that on top of all the other anomalies that vanish in the standard model, there is now also some new gravitational anomaly that also happens to vanish.
Yes, and more than that, because these anomalies are sensitive to the global structure of the theory. For example, the local physics of the standard model is compatible with 4 gauge groups, all of which have the same Lie algebra, right? SU2 plus SU2 3 plus U1. And for all 4 these choices of the global structure of the gauge group, these anomalies vanish for all 4 of these. And again, it's not trivial. It could have been, right? Could have been in principle.
That you selected one.
Yes, but it doesn't, as far as I know, which is kind of a bummer. But at least it was a non-trivial constraint. And this can actually constrain non-trivially some extensions of, beyond standard model physics that people came up with. Like there are papers where people study these anomalies for such BSM models, and they find actual non-trivial things to say. For example, there are some models that have certain discrete symmetry for protons. It's a complicated story. And the implications of these anomalies, which again, were not there otherwise, would have not been there otherwise, is that in these particular BSM extensions, the number of chiral generations is a multiple of 3, which is, it's something that would have not popped out otherwise from the regular anomalies. So yeah.
So just a question on that, when you say you vanish in the standard model, is that with right-handed neutrino or without a right-handed?
I think it's without.
So
But
if you
with.
put a,
No, but they would vanish regardless, as far as I know. Yeah.
why? Because why is a right-handed neutrino not to us?
So the reason is that as long as the small anomalies vanish,
Yes.
right, which is something we know how to check since decades, the possible anomalies of this type, the large, they're called Dye-Fried, if you want to check them out, Dye-Fried. They are classified by some mathematical invariants, cobordism groups. And if there are non-trivial possible invariants, then you actually have to compute the anomaly and see if adding, for instance, neutrinos changes the story. In this case, there are no such non-trivial invariants. Everything is 0 from the beginning, kinematically, which means that you don't actually have to compute any anomaly. I mean, if you do, you just get 0. So yeah.
But this cobordism group is then something that depends on the space-time manifold.
No, that's the thing. It classifies certain coarse-grained features of the possible manifolds. In this case, for anomalies, not of space-time itself.
For example, if you live on the sphere, what is the coordinate class in that case? Is it something that gives rise to anomaly? I mean, different manifolds. On some manifolds, there would be an anomaly. On others, they could not.
Right, exactly.
Right.
Exactly. So if the small anomalies cancel, the anomalous part of these large transformations of the manifold is not in the manifold itself, is in the equivalence class up to these coordinates. And moreover, this is not the space-time manifold itself. It's like a D+1 dimensional extension that codes the anomalies. But it's complicated, but the point is there are constraints. There's some physics in this.
My comments on this?
Maybe that's a premature question, or maybe you have examined it. To what extent does this constrain string theory compactifications?
They all non-trivially vanish, as far as we check. So in particular, I wrote a paper a couple of years ago about this in the context of the simplest 10-dimensional strings, including non-supersymmetric ones. And we non-trivially found that they all vanish. And then there are some other works by Tachikawa, and I mean, I can tell you the literature, but yes, they vanish.
Sorry, is that they all vanish for all compactifications?
Yes, because what happens is that if you this is a general story about if you have higher dimensional theory. If you have some anomaly, an anomaly-free theory in this sense, in the big D dimensions,
yes.
If you go to small d by compactifying on any smooth manifold, the anomaly is guaranteed to vanish. Now, the question is if you do something more singular, which in string theory you can do, and in the case of heterotic superstrings, it was shown that even if you do that, all anomalies vanish in all dimensions.
So when do they not vanish? What can't I do?
Right. So, for example, I was quoting these some BSM models. I don't know the details right now, but I can send you some literature. There are some, phenomenologically motivated extensions of the standard model.
What are they adding? Generally, they add new particles. So
yes, they add new particles.
And what type of new particles are dangerous?
Well, the ones I think there are some fermions that are related by a discrete Z3 symmetry, which is called proton triality in these models. And that's the dangerous bit. It tells you that in order to cancel these anomalies, you need to include these guys in multiples of 3 generations. That's the result. But you can cook up all sorts of models. I mean, an example known since the 80s, which is not quite related to space-time topology, but to gauge group topology, is the famous SU2 anomaly in 4 dimensions, right? You must have an even number of fundamental chiral fermions in SU2 gauge theory in 4 dimensions. One example.
So we have strayed a little bit from the main topic of
but this is unitarity.
This panel.
It's all about
There's some question from the audience at this point. Otherwise, I would like to ask something to Bianca, because yesterday and today, we've heard that at least some people here are willing to accept a little bit of violation of causality, as long as it is sufficiently suppressed or in particularly small space-time regions. And now you mentioned in your slides that if you try to define non-perturbatively your relational clocks, you find always that at some point they start running backwards in time. Now, can you put a scale to this phenomenon in the same way that other people did, like here, for example, Alexey put a characteristic length to this violation of causality?
I would look at the papers. I do think that scale will depend on how fast the clock is in the first place. How fast?
The clock must go at a rate of 1 second per second, so it can be faster or slower than that.
No, I mean, what I mean is how fast, meaning with that I mean, if you consider the bracket of the Hamiltonian with the clock system,
yes,
then typically you have a relativistic system. You get the momentum on that side. So, if that goes to 0, then that's what happens if the clock starts to go backwards. The problem is if it goes to 0. And there might be some prefactors.
0, what do you mean?
I mean, actually, the simplest example is the time of arrival operator. Books have been written about the time of arrival operator because it's difficult to make it self-adjoint. And so this is indeed, and if you think about it relational, instead of choosing t as your time, you choose the position as your clock.
Mm.
And then you express what is the time when the particle is at a certain position. But the issue with taking the position is that the momentum conjugated to the position can be positive and can be negative. So that can go also backwards. And so if you go to the quantum theory, then the issue is defining this expression, which gives you the time of arrival, as a self-adjoint operator. In this case, technically, you have I think we have a 1 over p, but it's also multiplied by 2 q's. And so you can make various choices for that. And I have to check that there's a paper by Ivano, Ivano, and others, which derived an effect which they called some uncertainty in energy and what the scale for that was.
So, but your picture is that this clock will start going backwards and therefore it's not a good clock anymore. We have to use another one, or will it start going forward after a short time? That's basically what I have in mind.
Boyewald indeed considered both things. He was called, back then he was calling clocks fashionables, because he indeed wanted to change to another clock that one, if the first clock stops working. And yeah, I think that will, but also what happens if you sit on one clock and turn backwards. But I think, if I remember correctly, in this paper it was more of they considered more indeed global clocks. And then you can also ask other question: what happens if you have only periodic clocks? Does it make sense to count the periods? I think we might say yes. I don't really agree. So there's a lot of literature also now quantum gradation about these relational aspects and what happens if we do not have perfect clocks.
Unrelated. It's not.
Well, yeah, I would have to check the literature if there's anything that would this. You know, but it will depend on your choice of clocks.
I do have like a question book. I mean, first for Alex and then for John. So I'll start maybe with Alex, who is there very quiet. So, in your short presentation, you said basically that you didn't have much to say about stability. But I do think that we should say something if we are taking infinite derivative gravity as an approach to, let's say, gravity, one that you presented today. Because, as you said, one of the main motivation to do something else, in your case, is to move from finite order derivative to infinite order was the orthogonality theorem, right? That's, say, the standard example to use, because orthogonality says that if you have some non-degenerate Lagrangian, you will have some, and high derivatives, we will have some unbounded Hamiltonian, which in general can cause instabilities, which is independent of the issue of unitarity. It's just a classical question. Now, I also understand that in your approach, what is more fundamental is quantum. So basically, you quantize your theory, try to make it unitarity by choosing some form factors which kill, or at least, let's say, remove the ghosts. But I think that it is still important to ask the question of, if you take a classical limit, what is basically, what is happening to the field equation? Do you still get runaway solution? Or what is the Hamiltonian of this infinite derivative system? And as far as I understand, the question of how to define an Hamiltonian is still not clear in this context, like how to define a ground state of your system. So I would like to know more about what is your opinion and why you think that maybe stability is not so relevant, maybe as compared to the other two.
No, I don't say that it's completely irrelevant. I just say that I have much less to say about this. But if you ask precisely what to do in theory in which actually, I didn't say that I define quantum theory and not have classical theory. Classical, everything is fine in this theory. And the basic point, even though I written many times that propagator is non-local, it is, if I capture my motivation from strings, propagator is totally local, but even in this gravity approach, I can make always field redefinition and make propagator as local. So it is local theory with non-local interaction, which can be treated perturbatively. In this treatment, there is nothing wrong. It's perturbative treatment of the interaction, where I have some coupling constant. It's exactly how it was done nearly 40 years ago by Witten in his paper on string field theory. Here I don't add anything, I just say similar construction is relevant for gravity, and stability of this system At classical level, propagator is totally local, well-defined. You can quantize it, and you can define your ground state quantizing free theory.
I agree, but
with
it is a perturbative statement. Like, for instance, if you take phi to the cube theory, perturbatively would say something the theory is fine, but non-perturbatively, I mean, it's unstable. So, I don't know.
This is why it is important to find out the upon quantization, to find out the full propagator and to find out what happens in non-perturbative regime if possible, but at least to find out full propagator, at least to find a running of constants, and then finally the hope is that we will come to some full propagator, which will be again up to filter definition, a local one. So I don't see issue with stability in this approach, because of higher, actually infinite derivative here is a trick which makes you possible to make filter definition. You cannot redefine stellar theory to 1 degree of freedom. You cannot redefine by square root of box minus m squared.
I think I agree on this. There is no issue. Is that the problem of, like, how do you define really an Hamiltonian in this case, not perturbativity? Because, I mean, you have a theory with infinite derivative, so naively you say I need infinite momenta, but maybe this infinite number of momenta will be not all.
You mean infinite number of initial conditions?
We know that in some simple case you can show that they are finite, but in a generic case where you have no linear interaction and derivative in both vertices and propagator, this is not clear. So one should really, I think, be worried about stability in this case, trying to understand better.
Yes, exactly. One should be worried, but we don't worry unless we kind of find the full and complete picture of the theory. If upon finding full propagator it behaves with wrong states, then we did something wrong in this approach. Okay? The expectation is that upon computation of full propagator in the theory, we will end up with something which can be, upon filter definition, brought to a local model with interactions. Okay? The definition of Hamiltonian is known in this case. The thing on the way are non-local interactions in bare action, which we will take care of upon completing the full.
Okay, so basically you're just saying perturbativity is fine. We can, I think I agree with that.
It's not like the thing is given and granted, and not like it's done, but we're working on this.
But still, I think the example of phi cube, which is in maybe, one has to, would be nice to have like some more progress towards understanding.
No, of course, but I didn't start with phi cube, okay? Fortunately. Or did I wrote today phi cube?
You did.
Yeah. No, I think the local case was 5.4. The local case, the potential was 5.4, yeah.
The local case was 5.4, I guess. But anyway.
That's the last thing. Because usually, if you have a theory, most of the cases we know how to write down at least classically an Hamiltonian, whether or not that is the physical Hamiltonian. Okay. But in that case, it's not even clear how to write.
Well, in gravity, usually we have trouble to write Hamiltonian in GR.
Even if you take a square model with infinite derivative, you don't know how to write down.
You want to speak about field theory. In higher derivative, it's the same problem as in higher derivative field theory. You will have the trouble to write Hamiltonian. Actually, it's a question which we are thinking about whether Hamiltonian as such exists. Okay? Let's put things clear. There is idea to just question whether writing Hamiltonian is necessary, unless you're really sure you know why you do.
You have another question?
Yeah, it's from John, but
okay.
Can I?
Go ahead.
Our organizer. I know we're late, maybe. Okay. So, John, actually, I'm very happy that you mentioned Starobinsky here on the fun part, because this is, I would say, the motivation I would use also to say that quadratic gravity maybe has some partial success, even observation. Okay. And yesterday you were asking at the end of your talk, is this success or what is success? Do you remember? No. I would say this is some type of partial success, right? Because we should not have like 100% success. This is a step by step. And I would maybe motivate even more saying, okay, we are just asking the same principle that we use for other interactions, which is basically strict renormalizability. And for free, you get extra contribution in the action that can be used to do also new physics beyond Einstein. Not only that, Starobinsky inflation, I'm not a cosmologist, but Starobinsky inflation seems to be, at the moment, the best fit we have for inflation. And this can be confirmed by some expert people. I would say this is something great, so that's why maybe let's try to understand more the other part of the Lagrangian, which is the white square term, instead of throwing everything away. And so in this respect, going back to the question of if this is true, and we take this point of view, then we should, of course, worry about the white square term, also phenomenological, try to understand maybe what does it do in the universe cosmology. And so let's assume we are in a situation in which matter is not there, because maybe we imagine that matter comes below the inflatons, below the 10 to the 13 GeV. So we are in a situation in which we have only the scalar field from the R square, and it's been to massive cost. And if we follow your, so sometime I think, what can this cost do during inflation? If it is high enough in mass, maybe we can decay in the scalar on itself, and maybe we can give some extra effects besides contributing to the gravitational perturbation, right? That also Ivano mentioned. So it would be nice to understand what type of new physics can give rise to this field. But if I follow what you said about the tachyonic free trajectory that you found with Roberto and Diego, in that case, the mass of the ghost actually is slightly smaller than the scalar degree of freedom. So in that case, I would not see the spin 2 decay in the ghost, because in the scalar, because maybe it's not kinematically possible. So you really have two fields which have the same mass and so on. So I would like to know what kind of new effect that could somehow be a consequence of some acausal violation, which is high energy acausal violation in that case. What kind of effect do you have in mind that could be an imprint in some observation like CMB or whatever?
Right. So what I if I actually had the actual thing, I would have, of course, published it right away. Okay. So I don't have it, but what I do have in mind is the fact that the usually we're restricted to interactions within the light code, and these theories would then not have that restriction. And so it'd be correlations that are outside the light cone that would be a signal that that's not causal. If we didn't know about inflation, we would have already said that maybe that's the case in the sky that we see now. We see that patch over there and that patch over there have the same physics. So they look like they're correlated, even though under causal evolution they would never be in contact. And so that if we didn't know that inflation could do it, this might have been an alternate explanation. And so the idea would be to somehow look for that in an inflationary theory, correlations that are causally not allowed. I'm starting to get fuzzy about it because I don't have the answer, but that's the goal.
It would be nice to,
because
if you measure the tensor square ratio, most likely you can fix the coefficient by square. It would be nice to have an additional prediction that will not, that basically will not fix any more parameters, because all the parameters are fixed. So that will be a sharp prediction.
Right. And if it is really causality, it's really sharp.
Yeah.
Okay. So Sarah,
first question. The short question in relation to this question, very short. Like basically, you have scalar on and you have a massive, right? Let's say it's not a ghost and some prescription allow you to escalate as not ghost and good state. But if you go to the important point is to understand how scalaron interact with this massive field and whether it can imprint in the CMB or cross correlations which people are aiming to measure in the next 20, 30 years.
Right.
This will leave a strong prediction, and maybe we can measure the effect of massive graviton. So that's just a comment. My question is to you, so actually. Well, you mentioned that this deepest problem in theoretical physics, your paper, I liked in your paper, but the question is related to that. So you mentioned that you see the problem of unitarity and everything comes at way below the Planck scales. Now, what is really, is quantum gravity of Planck scales is relevant for this problem or not? If yes, how? If not, why not? So,
okay. Sorry, I guess I'm a little bit confused about the question, but no, I think that, well, there are issues in defining unitarity, but if we want to sharply define unitarity in gravity, at least one approach is to think about the S matrix, basically. And then you can ask the question, okay, is the S matrix unitary or isn't it? And when you consider ultra-Planckian scattering and consider what we think are the dominant processes that contribute to that for small enough impact parameters, then we have a crisis of unitarity having to do with quantum black hole formation and evaporation. And for me, that looks like a major clue to what quantum gravity, what is going on in quantum gravity. Ultimately, that seems to strongly suggest that there's something very different from the local quantum field theory paradigm that we need to understand, that extends to long distances and not just short distances. That's the short version.
So, okay, let me rephrase it. So we need full quantum gravity and scatterings to really fully understand the puzzle that comes from QFT in curved spacetime.
Well, put differently, we can ask, well, what is the problem of quantum gravity? And one way to think about it is to try to investigate processes in extreme limits. And one extreme limit, which I think really seems to probe what is really different about quantum gravity, is the extreme limit of, say, ultra-Planckian scattering. Okay, and there, if we sort of naively think about how to describe that, we basically fall flat on our faces. As Hawking first explained, we have a massive violation of unitarity, apparently, if we just follow naively the local quantum field theory paradigm. So that's a place, that's an extreme limit where thinking about the physics seems to be telling us that quantum gravity has some very different behavior than properties of local quantum field theory.
Okay, thanks.
Okay, so we are a little bit over time, and I don't see any raised hands here. So 1, 2, and 3, and the discussion is over.